बिस्मिल्लाहिर्रहमानिर्रहीम। रब्बिश रहली सदरी व यस्सिरली अमरी वहलुल उक़दतम मिन लिसानी यफ़क़हू क़ौली। Assalamu alaikum. Today we will start chapter 2 of quantum mechanics by Beck. 2.1 Polarization. 2.1.1 The polarization vector. Chapter 2 Classical description of polarization. This chapter describes the classical theory of the polarization of an electromagnetic wave. Here we learn how to represent polarization as a two-dimensional 2D vector and how optical elements which affect the polarization are represented as matrices. By combining these concepts, we'll be able to calculate how a combination of optical elements will transform the polarization of a wave. The polarization is represented as a 2D vector and the optical elements are represented as matrices. We carry out the matrix multiplication to find the output. We are exploring classical polarization now because in chapter 3 we will be talking about quantum mechanics of polarization. It's easier to understand the quantum mechanics if you already know the corresponding classical physics. 2.1 Polarization 2.1.1 The polarization vector. An electromagnetic wave such as light wave consists of propagating electric and magnetic fields. The polarization of the wave is determined by the direction of the electric field vector. The electromagnetic field is transverse, so electric field E is perpendicular to the direction of propagation. Assume that a wave is propagating in vacuum in z direction so that its wave vector is given by k is equal to kuz. The magnitude of the wave vector is related to the wavelength lambda, frequency f, angular frequency omega of the wave given by k is equal to 2 pi over lambda, k is equal to 2 pi f over c, k is equal to omega over c, where c is the speed of light in vacuum. Electromagnetic field is a transverse field, which means that electric field is perpendicular to the direction of propagation. The electric field and magnetic field are also perpendicular to each other. C is equal to speed of light, F is equal to frequency, lambda is equal to wavelength, C is equal to F times lambda. That makes lambda the wavelength equal to C over F. K is the wave vector, it is equal to 2 pi over lambda. If we substitute the value of wavelength lambda, we get k is equal to 2 pi f over c. 2 pi f is the angular frequency omega. Therefore, we get wave vector k is equal to omega over c. Electric field can be written as E is equal to Ex ux plus Ey uy, where Ex is equal to E0x cos kz minus omega t and Ey is equal to E0y cos kz minus omega t plus phi. Here E0x and E0y are the amplitudes of the field in the xy direction. The phase shift phi represents the fact that these two components do not necessarily oscillate with the same phase. The polarization of the wave is determined by the relative magnitudes of E0x and E0y and by the phase shift. The electric field is a superposition of electric field in x direction and electric field in y direction. If Ex is equal to 1 and Ey is equal to 0, we get horizontally polarized light. If Ex is equal to 0 and Ey is equal to 1, we get vertically polarized light. If Ex is equal to cos omega t and Ey is equal to cos omega t, we get polarized light at 45 degree. If Ex is equal to cos omega t and Ey is equal to minus cos omega t, we get linearly polarized light in minus 45 degree. If Ex is equal to cos omega t and Ey is equal to minus sin omega t, we get left hand circularly polarized light. If Ex is equal to cos omega t and Ey is equal to sin omega t, we get right hand circularly polarized light. If Ex is equal to cos omega t, Ey is equal to cos omega t plus pi over 4, we get left-handed elliptically polarized light at 45 degrees. If Ex is equal to cos omega t, Ey is equal to cos omega t plus 3 pi over 4, we get left-handed elliptically polarized light at minus 45 degree. If Ex is equal to cos omega t, Ey is equal to minus cos omega t plus pi over 4, we get right-handed elliptically polarized light at 45 degree. If Ex is equal to cos omega t, Ey is equal to minus cos omega t plus 3 pi over 4, we get right-handed elliptically polarized light at minus 45 degree. I'm sorry I have taken this diagram from the internet, but it represents very clearly what's going on. If the two waves of electric field in x direction and y direction are in phase, we get linear polarization. If one is a sine wave and other is a cos wave, we get circular polarization. And if there is a phase difference between them, that for example 45 degree, then it is elliptical polarization. In equation 2.3, we have written the field in terms of cosine functions because it is a real physical quantity. However, it is more convenient to write the field in terms of complex exponentials with the understanding that we can always take the real part whenever we are interested in finding the true field. With this convention, the components of the field become Ex is equal to E0x exponential ikz minus omega t. Ey is equal to E0y exponential ikz minus omega t plus phi. We know the Euler's formula exponential ikz minus omega t is equal to cos kz minus omega t plus I sin kz minus omega t. The cos kz minus omega t is the real term and I sin kz minus omega t is the imaginary term. To find the electric field, we'll only consider the real term. Similarly, exponential ikz minus omega t plus phi is equal to cos kz minus omega t plus phi plus I sin kz minus omega t plus phi. Again, the cos kz minus omega t plus phi is the real term and I sin kz minus omega t plus phi is the imaginary term. To find the electric field, we'll only consider the real term. And the total field is E is equal to E0x exponential ikz minus omega t u of x plus E0y exponential ikz minus omega t plus phi u of y. We can also call E0 as E naught. The amplitude of E naught of the field E is E naught is equal to under root sum of E naught x square plus E naught y square. We know that electric field is the sum of electric field in the x direction and electric field in the y direction. Therefore, E is equal to E naught x exponential iota kz minus omega t u of x plus E naught y exponential iota kz minus omega t plus phi u of y. Ux and Uy are unit vectors. If we take the conjugate of electric field, the iota becomes minus iota. Therefore, E conjugate is equal to E naught x exponential minus iota kz minus omega t u of x plus E naught y exponential minus iota kz minus omega t plus phi u of y. Electric field square is the dot product of E conjugate and E. The exponential terms cancel and we are left with E naught x square plus E naught y square. To find E naught, we take the under root. So E naught is equal to under root E naught x square plus E naught y square. In terms of amplitude, the field is, we'll multiply the electric field by E naught and we'll divide the electric field by E naught. We will take exponential ikz minus omega t as common. We are left with electric field is equal to E naught exponential ikz minus omega t brackets E naught x over E naught u of x plus E naught y over E naught ei phi u of phi. We define the polarization vector epsilon naught to be equal to the quantity in brackets in equation 2.7. Epsilon naught is equal to bracket E naught x over E naught u of x plus E naught y over E naught ei phi u of phi. In general, this is a complex vector. It is also a unit vector. The magnitude of epsilon is equal to under root dot product of epsilon conjugate with epsilon. This is equal to under root E naught x over E naught whole square plus E naught y over E naught whole square. Since E naught x square plus E naught y square is equal to E naught square, we get under root E naught square over E naught square. That gives us 1. The electric field can be written in terms of polarization vector as E is equal to E naught exponential iota kz minus omega t epsilon. If we substitute equation 2.8 in equation 2.7, we get equation 2.10. In equation 2.10, there is no x or y dependence. The field is constant over any plane perpendicular to the propagation direction, the z-axis. A field of this form is called a plane wave. An optical detector does not respond directly to the electric field, but instead to the power incident on it. This is because electric field oscillates very rapidly in optical region of the spectrum. Detectors cannot follow these oscillations and instead average over many oscillation periods. The power is proportional to the intensity, which we'll define to be equal to the square magnitude of the field. Intensity is equal to magnitude of electric field square, which is equal to electric field conjugate dot product with electric field. The intensity doesn't fluctuate at optical frequencies. This fact can be seen in intensity is equal to electric field conjugate dot product with electric field. This is equal to E naught exponential minus I kz minus omega t E conjugate dot product with E naught exponential I kz minus omega t epsilon. The dot product of epsilon conjugate with epsilon is equal to 1, and an exponential minus iota kz minus omega t dot product with exponential I kz minus omega t is equal to 1. Therefore, we are left with E naught square, which has no oscillatory time dependence. The intensity follows slow compared to detector's response time, fluctuations in field amplitude E naught, but not oscillations at optical frequencies. Detectors effectively respond to intensity defined in equation 2.11. The intensity is equal to amplitude of electric field square. It does not depend upon optical frequencies since detectors are not fine enough to observe them. May Allah bless us all. Thank you for watching. Allah Hafiz.